So, welcome everyone. This is TLE Eliminators, and we are going to discuss the code forces round 955 today. So, I am your mentor Abhinav. Let's get started. Okay, so the first problem is soccer, and Dima loves watching soccer in such a game. The score of the scoreboard is represented as X is to Y, where X is the number of goals in the first team and Y is the number of goals of the second team. At any given time, only one team can score a goal, so score XY can change to X plus 1 Y or XY plus 1. So while watching a soccer game, Dima was distracted and this and that. So Dima remembers the score right before he was distracted and the score right after he returned. So given these two scores, he wonders the following question. So you are given the scores of a football match, soccer match. So you are given scores at two times, at the time where before he was distracted and at the time after he was distracted. Two scores you are given, and then it is asked, is it possible that while Dima was not watching the game, that teams never had an equal score? Okay, so the thing you have to notice that it's asked, is it possible? So in any case, if it is possible that the scores of the two teams was never equal in between the two times the scores are given, then you have to print a yes. Otherwise, you have to print a no. Okay, so like if you we try to understand it more clearly, so it's given that uh, okay, so you are given the you are given four integers x1, y1, x2, y2. So x1, y1 represents the score at some time. Okay, sorry, x1, y1 and x2, y2. You are given four integers. X1, y1 represents the score at some time, and x2, y2. Sorry, what's happening? Just a second. Okay, sorry, there was some glitch. Okay, so like we have x1, y1, and x2, y. So x2, x1, y1 represents the score at some time, and x2, y2 the score at some other time. So like if we are given 3 is to 0, this is the score at some time, let's say t, and then at some time t1, and then at some time t2 the score is given, let's say 5 is to 1. Okay. Now what you need to find is in between these two times. Okay, so the from reaching 3-0 to 5-1, in between there would be more scores because the score is always increasing by one. So from 3-0 it may go to 3-1, then 4-1, then 5-1, like this it may go, or through some in between process it would go. Now you have to find out, is it possible that these scores in the middle, among them, like if both the scores are equal, that thing is like never happens. If it is possible that from 3-0 to 5-1, never in between the scores became equal. If that is possible in any of the case, then you have to print a yes, otherwise a no. Okay. So what does it basically mean? When would it happen that, let's say you have some score 3, 2, and then the final score is, let's say, 4, 5. Okay. Now, if you want to reach from 3, 2 to 4, 5, in between the scores, because here in 3, 2, the team A is leading. I'm saying this as team A, this is team B. In this, the team A is leading. And in this, if you see, the team B is leading. So when the lead goes from A to B, then it is for sure then in between there would be a time when A would be equal to B. Because without that, B cannot surpass A. If B has to surpass A, then first B A and the if A is greater than B, then first A would have to become equal to B, then only A can become less than B. So if it is a case where one team is leading at the time t1 and at time t2 another team is leading, then in that case it is for sure then that in the between we would get some either 3-3 unequal score or a 4-4 unequal score. We would get some equal score, this is for sure, because without that we cannot. So in this case we would give a no, and in all other cases we would just give yes. So is the logic clear? So if let's suppose team A is leading at T1, if team A is leading, and at T2, again team A is only leading, then the lead is not changing. Then we can make a sequence where always A is leading and the scores are never equal. In that case, we would give a yes. But if we have a case where at T1 team A is leading and at T2 team B is leading, then it is for sure then that in the middle we will get a score where both the scores are equal. So in this case, we would print a no. Okay, so is the logic clear here? Okay, so it's very simple. You have to just check that if at the initial condition, you have to check if x1 is greater than y1 initially. And so this, if this is true, then team A is leading. If this is false, then team B is leading. It's simple. It's also given in the question that in these two timestamps, the scores are not equal. The scores are always unequal. So it is guaranteed that at neither of the two time points, DEMA remembers the teams had equal scores. So it would never happen that x1 and x2 are like x1 and y1 or x2 equal to y2. This case is never given to us. It's mentioned in the problem only. So either x1 would be greater than y1 or x1 would be less than y1. So if this is the case, if this returns true, then team A is leading. If this returns false, then team B is leading. And then we would check x2 greater than y1. So if this case returns true, then team A is leading. If this case returns false, then team B is leading. Now we can compare these two. So if both of them are true, then this means team A is always leading. So we would give yes. If both of them are false, then team B is always leading. We would give a yes. But if one is true and one is false, then the uh, means first team A was leading, then it went to B, or team B was leading, then it went to B. So we can just check if x1 greater than y1, this the true or false this boolean value, if it is equal to x2 greater than y1, this boolean value, then in that case we would just print a yes. Otherwise we would print a else. We would print a no. Okay. So simply we have to just check this in our code. Okay. So you can now see the code. Okay, let me zoom it a little so it's more clear. Okay, so it's simply we have taken four variables A, B, C, D, and we just checked. So A, B was x1, y1. If x1 less than y1 is equal to x2 less than y2. If this condition is satisfied, then we would print a yes, otherwise a no. So this yes no function just does that. If it gets true, it would print yes, otherwise it would print no. Okay, so we are just a one-liner code. If this condition is satisfied, we would print a yes, otherwise a no. And its time complexity would obviously be O of 1. It's simply a constant time thing. Okay. So I hope the first problem is clear. It was pretty easy. So we can now move to the second problem. Okay. Okay. So let's move to the second problem. Collard's conjecture. So recently, the first year student Maxim learned the Collard's conjecture. So if you don't know about Collard's conjecture, there's no problem. But if you wish to know about it, if you have an interest in mathematics, like you can actually search about it. It's very interesting thing. But in this problem, that's not required because we are not given the actual Collard's conjecture, but something else. So let's see what we are given. He didn't pay much attention during the lecture, so he believes so like this is what we are given here. It's not the actual collage conjecture. If you search about it, it's really interesting thing if you have interest in mathematics. But let's discuss this problem now. there is a variable x and a constant y. The following operation is performed k times. So like here, what we are given two variables, x and a variable and a constant y. So now each operation, what we are doing, we would increase x by 1 first, and then we would check while the number x is divisible by y divided by y. So until the time x is divisible by y, just divide it by y. Okay, now after these two things are performed, this is counted as a single operation. Okay, now you have to perform this operation k times. Okay, and then after performing this operation k times, you have to tell the final value of x, what you would get. Okay, so like an example is given. If x is 16, y is 3, and k is 2. Okay, so in the first operation, x would be plus 1. So 16 would become 17. And then we would check if 17 is divisible by 3. No, so we would not do anything. So after first operation, x becomes 17. Then next operation, 17 would be increased to 18. And then we would check if 18 is divisible by 3. Yes, we would divide it by 3. So it becomes 9. Again, 9 is divisible by 3. We would divide it by 3. It becomes 3. Uh, 18 by 3, sorry, 6. 18 by 3, we got 6. And then 6 is divisible by 3. We got uh, dividing by 3, we got 2. So we got 2 as the final value after two operations. So with these values, our final answer would be 2 because we are getting 2 as the final value. So this is what we have to perform. But like if you do it directly, if you perform the k operations, like you can perform each operation, do a plus 1 and then divide until it's not equal. If you do 1 by 1, then k is 1e9. So you cannot do all the operations 1 by 1 because O of 1e9 would give you TLE. So what you can do, okay, so what you can do, and let's see. Okay, let's take an example. One motor, let's take 2455, or let's take anything. So like, okay. So now what we are given? We are given three variables, x, y, and k. Okay. So what we need to do? So let's suppose we are given x equal to 15 and let's say y equal to 4. Okay. And then we have to perform this operation some number of times, let's say 5 times. Okay. So what you would do, first operation, what you would do, x is 15. So first increase it by 1, make it 16. Then check if that value is divisible by y. So 16 is divisible by y. What we would do? We would make 16 by 4, 4. 4 is still divisible, 4 by 4, 1. So after first operation, x becomes 1. Now we would apply the second operation. So x is 1. Now we would increase it by 1, make it 2. And now 2 is not divisible by 4, we would stop here. So x is 2 after the second operation. So likewise, we would perform the third operation, make x from 2 to 3. 3 is not divisible, we would stop. Fourth operation, x is 3. 3 is made 4. Now 4 is divisible by 4, it would again become 1. Then after the fifth operation, x is 1 and it would be increased by 1 to become 2. 2 is not divisible. So finally, the x we got is 2. So 2 would be our answer in this case. So like this we have to do, but how can we optimize it? That's the problem here. Because if we perform 1 by 1, it's O of k, which is not accepted. So we need to optimize it. So if you take a closer look, what is happening here? Okay. So let's say you have some y. Okay, I'm writing down the numbers. So like what condition you are checking? Whatever x you have, you first make it x plus 1. And then you check if x plus 1 is divisible by 1. That's what you check. So if you like in a, let's say we are writing all the numbers, let's say 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's say it represents a number line. In a number line, we are writing all the numbers. Okay, let's take a number line. Okay, whoever is doing that, let me, please don't do that or I have to. Okay, so now if we have a number line, so now let's say we have all these numbers. Now what we have to check? We have to check whether x plus 1 is divisible by y. So we can just, let's say we write down the modulo y below. So it would be 0, 1, 2 up till y. Let's say y is 5, then here up till 4 we would have a 4, and then it would again become 0, then 1, 2, 3, then 4, then 0, 1, 2, 3. It would go like this. This I am writing the modulo y of every number. So now let's see. If I am at say x equal to 2, what would happen? I would move from 2 to 3, and then this I would check. If this is 0, this modulo y, if this is 0, then we would divide it, otherwise we would let it be. Okay, so let me write the 3 here. So if we are at x equal to 2, then after one step you would move to 3 and stop. Then if you are at 3, after one step you would move to 4, but then again you would stop. After 4 you would move to 5. Here you got it is divisible by y. Then you would divide 5 by 5 and move to 1. Okay, if you are at some higher value, let's say, let me write this 9, 10, 11. Okay. If you are at some higher value, let's say you are at 8. Okay, you after one step you would move from 8 to 9. After next step you would move from 9 to 10, and after 10, since you would not stop at 10, since 10 is divisible by 5, you would divide 10 by 2 and move to 2. Okay, and then from 2 you would move to 3, 4, 5. Now from 5 you would move to 1, then 2, 3, 4, 5, then 1, 2, 3, 4, 5. Once you reach 1, you would come in a cycle. You can recognize that. If you are at 1, you would move 2, 3, 4, then 1, 2, 3, 4, then from 5 you would move 1. So you would get into a cycle after you reach 1. That's the first thing. Now, but if you have some really big number, okay, then till you reach 1, you would have to do something. So like, how can you do? What you can do? So the first thing you can recognize, we can just divide it into like groups. If you have y equal to 5, you can divide it into groups of 5. Okay, you would have groups of 5. So if you are in some group, okay, let's say this is group 1, this is group 2, this is group 3. If you are in group 2, okay, then at once, if you are at 7, you can say that you would need 2 more steps to reach the end of the group, and thus when you reach the end of the group, you would be reduced to something. Okay, if it is sorry, from here you would reach 10, and then you would get reduced to 2. Okay, so if you are at 7, just by looking at the modulo value, if it is 2, it means 5 minus 2 equal to 3. You would need 3 more steps to reach the end. So you can just, instead of doing it 3 times, in one time you can say that if you do modulo y, then y minus x modulo y, this value. Okay, so modulo y was 2, y minus x modulo y was 5 minus 2 is 3. So if you do y minus x modulo 5, these would be the number of steps needed to reach from to the end of the group you are in. So after these many steps, so if you are at 7, after 3 steps, you would reach the end, and thus from the end, you would now reach, if this group number is 2, that is 10 by 5 is 2, you would reach to 2. Okay, so you would fall down to some other group. Okay, you would not remain in this group now. Now, how much will you fall? Like, now this thing you can calculate in one step. You can just, these many steps can be done in one step, and then you can reduce your x to until the time you fall. So like 10, if you are at 10, then 10 by 5 to 2. Again, you can check 2. If 2 is divisible by 5, you can reduce it more. So like in one operation, you can calculate, you can do these many operations on k and then reduce it, divided by k, divided by y. You at minimum, you would divide by y. Now, in how many steps would you fall to group 1? If you think about it, if you are at some very big value, let's say 1e9, and y is something 5, Okay. So in one step, like you can calculate the modulo or do that much, and then the number would still remain somewhere in 29 range only after doing this plus minus 2, 3, whatever. Then you would divide by 5. Okay. Now whatever number you got, you would again divide by 5. In each operation, at minimum you are dividing by y once. So in how many operations would you reach this 0? If you try to calculate in log of x operation to the base y, in after these many divisions, you are sure you would reach this first group. Okay. So you can just compute this in log of x complexity. You can say in log of x steps, you would reach group number 1. Now, once you reach group number 1, you know it's going to follow a cycle. If you are at, let's say, 1, you would follow this cycle. Sorry, from if you are at 1, 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5. After that, it's going to follow a cycle. So then for the cyclic thing, you can just compute it again in O of 1, that where you would reach after k steps. Okay, so that also we would discuss how you compute. So like you got the feeling how you can reduce this from O of k to O of log x actually, and x is 1e9, so log of 1e9 would be accepted. Okay, so let's again now with an example see what actually we are doing. Okay, let's say you have x, let's take some bigger value now, let's say you have 34. Okay, now y is something 3 and k is, let's suppose, some 200 steps we have to do. Okay, now since x is 34, now if you see on the number line, first y is 3, you would divide this in groups of 3. Okay, so let's say x is somewhere you have 34. Now if you divide it in groups of 3, so first thing you would calculate where would that group lie. Here you have 33, you have 35, you have 36. So this group would be, so if you write the modulo y, it is 0, 1, 2, 0. So this would be the group, okay, to which 34 belongs. Okay, now what you can do, you can just move to the end of the group in 2 steps, and then from 36 you would do by 3 and reach 12. 12 you would do by 3 and reach 4. So after, so in one step, what you would say, if I am at 34 using 2 operations, so using 2 operations I can reach, so I would reduce k by 2 from 200. I use 2 operations, now 198 operations remaining. And after 2 operations, where would I reach? And how I calculated 2? 2 was y minus x modulo y. Okay, so y was 3. So 3 minus 34 modulo 3 was 1. We got 2. Okay, so in 2 steps, we are reaching the end. That's the first thing I said. So I would reduce k by 2. And where we are reaching? From 36, again, we would divide by 3 and reach 12, divide by 3 and reach 4. So we are reaching 4. So we would say in one operation only, we would just perform these 2 steps, and x is now from 36 to 4. We have reached to 4. Okay, so now x would be here. Okay, so this 34 is reduced to 4. K is so in 2 steps we got to 4. Now again we would do, so like if you see, we have 3 here, 4 here, 5 here, 6 here. So this is a group. Now again we would calculate y minus x modulo y. What is that? That is 3 minus 4 modulo 3 is 1, it is 2. Again you would take 2 steps to reach something divisible by k. So after 2 steps we will reach 6. Now, so first thing we would do, we would reduce 2 steps from here. 1, it would become 196. Now, after 6, what we can do? 6 by 3, 2. 2 is not divisible by 3, so we reach 2. So from here, we can say we have reached to here. So now x is from 4, it has become 2. Now this is our next step. So x has become 2 and we still have 196 more steps. Okay. Now when we are at 2, again we would calculate this value. It would be 3 minus 2, 1. So in one step we would reach the end. So in one step, we would reach 3. So 198 is reduced to 1. So we reach 3. And from 3 by 3 is 1. We again got to 1. Now, once we get to 1, we would stop here because now we know we can, it would move in a cycle. Okay, it would move in this cycle. So that whole cycle thing we would calculate in one step. Let's see how we are going to calculate. So now X has become 1 here and we still have 195 more operations. So now what you have the new step that X is now 1, Y would remain 3 only. This is a constant. And we still have 194 more, 195 more steps. Okay. So now let's look at the cycle we have. Okay. What cycle we have? We are at 1, 2, 3. So in one step, we would reach 2. Next step, we would go to 3 and 3 by 3, 1. So in one step, we would reach 2. And from 2, we would again reach 1. 2, 1, 2, 1. This way we would reach. So if you have 195 steps, after every 2 steps, we are reaching 1. So you can just, what you can do, okay, what you can do, you can just divide this, you can take a remainder of 195 modulo 2 because 2 to 2 steps are common. After every 2 steps, I am reaching 1 again. So 195 can be reduced to 193, 191, likewise, till when it would be reduced? It would be reduced up to 195 modulo 1 till it reaches 1. So we can reduce k to k modulo equal to 2. What is 2 here? It's actually y minus 1. Let's say if you had y equal to 4, it would take, if you had y equal to 4, it would take 1, 2, and then 3 steps. So it's always going to take y minus 1 steps. It's a cycle of y minus 1 steps. So you would do k modulo equal to y minus 1 here. Okay. And then whatever remainder you get, so if you get a remainder of 1 here, it means one more step you have to perform. So you would add 1 to x. So x would become, from 1, it would become 2. So 2 would be your final answer. That's it. Okay. So is it clear how you, could you prove how log yx we can reach proof 1? Could you please prove? Okay. Okay. Could you please prove? So like, if you did not understand why I told it's log of x with base y. So I can prove that. Let's suppose you have some very big x. Okay. Now, what you are doing in each step, first you are making x, what you are adding x plus equal to y minus x modulo y. So these number of steps, you are first adding the number of steps to y. So this thing would be less than y for sure. Okay, x modulo y is less than y and y minus less than y would be less than y. Okay, so like less than equal to y steps you are adding to x. So now x would become at max x plus y. Okay, that is the thing at max it would become. What actually I'm saying, to whichever group x belongs, the modulo y groups I have had written, it would go to the end of the group. Okay, first thing. Now, once it reaches the end of the group, it would be divided by y continuously. So in each step, now to whichever group it belongs, if you give a number to that group, how many groups can you have? You can have x by y groups if you look closely. Like the groups I had written here, these groups 1, 2, 3. So you are dividing in the groups of y. So at max you would have x by y groups. Okay. So let's say at worst case y is 1, then you would have x groups. Okay. So in worst case you would have x groups. Okay. Now in each step what we are doing, we are making x to x by y. So in each step we are going from group number x to group number x by y after first step. Okay. Now after second step, we would go from x by y to x by y again. So it's x by y square. After third step, we would move to, okay, x by y to x by y square. We would move to x by y cube. So after ith step, you can say we would move to x by y to the power I. You can say that. Okay. Whoever was asking the doubt, just tell me if it's clear till here. Okay. After I steps, you would reach not clear. Okay. Okay. You can unmute also and say where it was not clear. Like, did you understand this grouping thing? You can just unmute and say if it's more
Yeah,
comfortable to
like
you.
I understand the grouping part.
Yeah.
Where I'm stuck is like, let's suppose we are in a particular group,
Yeah.
and at each step we are dividing it by y, right?
Yeah.
And but you mentioned that in order to reach the first group, it will take log x y, or I think
Yeah.
log y
So,
x.
yeah.
That part I
So,
didn't
that's
understand.
what
Like,
yeah. That's what I'm like till here, what I explained. If you are at group X, after first step, you would move to X by Y. After
yes,
second step, you would move to X by Y square. After third step, X by Y cube. So after ith step, you would move to X by Y to the power I. Is this thing clear?
not really, right? So in the first step, like if I reach the end of the group, then x will be
Yeah.
divisible by y. So I'll move
Yeah.
back to the previous last group. But it's not necessary that it will be divided by y square as well, right?
No, what I am telling, let's say from X, you first reached to X plus something which was divisible by Y. Okay. So if
Correct,
X was not divisible, you reached to X plus something. So this X and X plus something would be nearly the same, not much difference. Because if you divide X
correct.
by Y or X plus something by Y, integer division of both of them is going to be the same. So you can
Yes,
write
correct.
x plus something by y as x by y. Okay. So now once you reached x by y, now whatever value you have, let's say this is x dash, again you would reach x dash plus something and that you would divide by y. This again I can write as nearly equal to x dash by y. In integer division, both of them would be equal.
Okay, so the
Is this
step
clear?
that we are saying is basically like
Yeah, because
moving from each group.
yeah, because plus something what we are doing, this we are calculating in O of one only. So like
Correct,
one operation would be just calculate this thing and next operation divide by this. So like two operations is O of constant operations only. So in constant time, we are moving from x to x by y, then x by y to x by y square, then x by y cube. Like this thing is clear. In I steps, you
yeah,
can move to x by y to the power I.
yeah, clear now.
Okay, so in I steps, so when would you reach one? If x by, I'm saying after I steps, you reached one. It means x by y to the power I is one. It means x is equal to y to the power I. So I is log of, you can write x with base y.
Base y, yeah, makes sense.
Okay, so this would be the time complexity. In I steps, you can reach here.
Got it, yeah. Thanks, Abhinav.
Okay. So can you explain k equal to k modulo y minus 1? Okay, let's come to on this thing. Why we did y minus 1. Okay, so once you have reached 1, now in log x time, you can reach 1. Now, once you have reached 1, okay, let's say you are at 1 now. Now, let's say y is some variable y only, 2, 3, 4, y. Okay, now what cycle would you have? Okay, you would have this cycle. From 1, you would reach 2, 3, 4 till y, and from y you would get back to 1. So how many steps did it took? If you look carefully, one step to reach 2, two steps to reach 3, three steps to reach 4, x steps to reach x plus 1, and y minus 1 steps to reach y. Okay, like in one step you reach 2, in two steps you reach 3, in three steps you reach 4. In how many steps would you reach some value I? In I minus 1 steps you will reach I. So in y minus 1 steps, you will reach y. After that, you will just divide y by y and make it 1. So it's a cycle of y minus 1 steps if you look closely. So after every y minus 1 steps, you are again getting back to 1. So if you are getting back to 1 after every y minus 1 steps, it means you can, and you have to do k more steps here. So if you have to do k more steps, and after every y minus 1 steps are neutralized, so you can just reduce this k by y minus 1 each time until you get k less than y. Till the time you have k greater than y, you can just do k minus equal to y minus 1. So what you would get finally, it would be k equal to k modulo y minus 1. This is the thing you would get, like if you just keep reducing k by y minus 1, y minus 1, y minus 1 until it's less than y minus 1. You would get this thing only. Like, is this clear? Whoever was asking this doubt. Okay, clear. So so we can just do k modulo equal to y minus 1, and now whatever k we are left with, it is less than y minus 1. So now we would just do x plus equal to k. So those many steps x would increase more, and that would be our final value. Okay, so I hope the logic is clear now. We can move to the code. Okay, so as I explained, first I took the xyk input, and then first thing. Okay, so till when would we run our loop? Either the operations get finished, either k becomes 0. So till the time k is greater than 0, we run our loop, or if x becomes equal to 1. So if till the time x is greater than 1 and k is greater than 0, we would run our loop. Once either x becomes equal to 1, we are reduced to 1, then we will calculate the cyclic thing afterwards. Or if the number of operations is finished, then also it's okay. Okay, so the while loop is still here. Now what we are doing, y minus x modulo y. As I told, these are the number of steps you would take. So if we are at some x of some group, to reach the end of the group, it would take these many steps to reach the end of the group. Now, these are the steps. Now, if it's taking these many steps to reach the end of the group, and if these steps are greater than k, so the number of more steps we have to do is less than the this remain the steps needed to reach k. So we won't do all of these steps. We would only do k steps, and k would become 0, and we can just break out of the loop and print our final answer. So this would become our final answer if k is less than the number of steps needed to reach the end. Okay, so this is the first thing. And if k is sufficient to reach the end, then we would reach the end. Then how much my x would increase? My x would increase this by rem. So we would reach the end by increasing it by these many steps. We would reach the end of the group, and then k would get reduced by these remaining steps. Number of steps we did, so k would be reduced by this thing we did. Now, if x has become divisible by k, so until the time x has become divisible by y, so until the time it's divisible by y, we would reduce it. Okay, so this thing we would perform. This is what we are doing in one step. Then again, we are repeating this process until we reach either x becomes 1 or the number of steps gets over. Okay, so I hope this inside thing is clear. Then once we reach x equal to 1, so if we have, after coming out, if we still have k greater than 0, we still have more steps. It means we would do the cyclic thing now. Okay, so first, what, as I had explained, we would do k modulo equal to y minus 1. So if k is very big, it's going to do y minus 1, y minus 1 times. We would just reduce it, because after y minus 1 steps, again, we are getting back to 1. So it doesn't matter. We would do k modulo equal to y minus 1. Now, whatever k is remaining, we would add that to x. And if it becomes divisible by, actually it won't, like this thing was actually not required. If you look at that time, I had written this, but you would get your final answer after doing this, or after doing y minus 1. Yeah, you would get your final answer. If it's y minus 1 steps only, k modulo y minus 1 would become 0, and you would add plus 0. So this thing was actually not required. Okay. So till here, and then you can just print your x. Okay, so this was the code. I hope it is clear. If you have any doubt in the code, or any part in this problem, you can write down now. Then we would move to the third problem if it is clear. Okay, so we can move to the third problem now. So in problem C, what we have, on another boring day, Igor got bored and decided to do something. But since he has no friends, he came up with a game to play. Igor has a deck of n cards. The ith card from the top has a number AI written on it. Igor wants to play a certain number of rounds until the cards run out. In this round, he takes a non-zero number of cards from the top of the deck and finishes the round. If the sum of the numbers on the card collected during the round is between L and R inclusive, the round is won, otherwise it is lost. So what we are actually doing here is Igor has some deck of cards from top to bottom, they are arranged. And what he is doing, he would just pick some non-zero number of cards from the top. So from the top of the deck, he would pick some number of cards. And if the sum of those cards, okay, the arithmetic sum of those cards is between L and R, then that round is won by him. Again, he would repeat this process until there are no cards left. And so you have to determine the maximum number of rounds he can win. Okay, so you have to find out what is the maximum number of rounds he can win. So you have to pick the cards optimally so that the number of rounds he wins is maximized. And note that the Igor is not required to win rounds consecutive. So it may happen he may win a round, then lose, then win, then lose. So it's not required to win consecutive. So this is the problem. Okay, let's try to understand the problem statement a little more clearly. Let's take this first test case. Okay, so what we are given here, we are given a deck of some cards from top to bottom is given. So we have 1, 2, 11, 3, 7. Like this, we have from top to bottom. Okay, this we are given. Now, what's also given is, what was this? Okay, what was this 10? L and R. Okay, so L and R we are given. So this is our L, this is our R. Okay, so what Igor has to do, he has to select cards. So let's say he selected the first two cards. Okay, now the sum of these 2 plus 1 is 3. Now, if this 3 falls in the range from L to R, then he would win the round. Otherwise, he would lose the round. That's the condition. So in this case, if he picks first two, then 2 plus 1 would be 3. And this 3 falls in the range L to R is 3 to 10. So this 3 falls in this range, so he would win this round. Okay. Now, let's say there is an 11 here. So if he picks just 11, 11 would anyways exceed 10. So it would not fall in the range from 3 to 10. So he would definitely lose here. Okay. Now let's say he selects just 3, or he can select 3 and 7 both. Okay. He has choice. So if he selects just 3, still it falls between 3 and 10. He would win. If he had selected 3 plus 7, it would be 10. Still he would win. But if he selects 3 and 7 separately, for 3 also he would win, 7 also he would win. So he can get 2 wins from here. And from 2-1, he got a 1 win. So maximum wins would be 3 here. Although he could have selected this 3 and 7 together and get 1 win only. But what you have to do, in this case, he would get only 2 wins. But you have to maximize the wins. So the maximum number of wins he can get would be 3. Okay. And you cannot include this 11 because if you include this 11 in any of them, it would be a loss for sure because that is greater than 10. So what you basically have to do is you are given an array. Okay. Now you have to divide this array into some groups. Okay. So these groups just represent that first he picks this much cards, then this much cards, then this much, then this much, then this much. Okay. So you have to divide this, partition this array into subgroups, and you have to partition it in such a way so that for each group you would calculate the sum. You would calculate the sum. If this sum is in between L to R range, then you get a win. Otherwise, you get a loss. Now, if let's suppose you get a win for this round, loss, win, loss, like this, then the number of wins you get, it's three in this case, you have to maximize these number of wins. So you have to partition them in such a way so that you maximize the number of wins. That's simply the what the problem statement is saying. So now, how can you do that? Okay, prefix sum from plus binary search someone is writing. Maybe I did it a little differently. Okay, so I have not used binary search. Maybe binary search can also be used. I can think of that. But now I'm explaining what I did. So what, like, okay, like first intuition, what you get from here. If you have some array, okay, let's take this only 2, 1, 11, 3, 7. 2, 1, 11, 3, 7. Okay, if you have something, now you want to basically divide it into groups so that the sum falls between the range of 3 to 10. L and R is given as 3 to 10. This is the range. You have to make the sum to fall in this range. Okay. Now, if you start with sum 2, okay. So if you include this 2, now definitely you would have to include every number in some group, but there would be some groups where you would win and there would be some groups where you would lose. So for the groups you lose, let's say you have some a group of three numbers, which like in your final optimal answer, let's say you are losing for all these three numbers, either you, so it would not matter whether you make all of them in a single group or separate groups like this or like this, whatever division of these you make, if these are not included in wins, you can just consider them as rejected numbers. Okay, you can just one by one reject them. You don't need to form groups for them. Okay, so you only need to form groups for the wins. You have to, so from this array you actually have to form some uh, groups which are non-intersecting groups. Okay, so you have to form some non-intersecting groups with sum in the range of L to R. So the sum of those groups, all of those groups should be in the range of L to R, and you have to maximize these number of groups. That's what the problem is actually. For the remaining part where you are losing, it doesn't matter. You can just consider them as rejected parts. Okay. So now the thing is, for each number you have to decide whether can you make a group, a winning group with that number, or would that be rejected. That's what you need to decide. Okay, so how can you do that? So first you take 2. First you will consider that we can make a winning group from that. So now if you just look at 2, it's less than L. So it's less than L. So like you would need more numbers to satisfy a condition. So you would move ahead. You would move to 1. So you would add 1 to 2. You would make it 3. Now what you saw, you are in the range. You made it equal to L. You are in this range. So if you are in this range, you already have a winning group. Now it's your choice. Maybe you, if you had, let's say, a 4 here, you could have included that 4 and made it 7. That was also a valid combination for here. But is it actually needed to add that 4? If you already have a winning group with these two numbers, why include that 4? You can utilize that 4 for some other group where you can have a winning combination. Or if this 4 cannot be utilized for some other group, it would remain rejected. There's no problem, because if you include that 4, you would still have one win. If you don't include, you would still have one win from this. But by not including, you may increase your chance of having one more win using that 4. And if you can't, then you can just reject it. No problem. So you would always try to include the minimum group. Okay. So you try to make your group to reach this value with minimum numbers. That's what you are going to try. Okay. If you think a little greedily. So you can just start from the first number and sum up until you get greater than equal to 12. Once you get greater than equal to 12, now there can be still two cases. Either after including this, you fall in this group that it is less than equal to R also. Okay. Or after including this, it exceeded L also and it exceeded R also. It may also happen if instead of 1 you had an 11 here, then 2 was less than L. And once you added 11, it would go greater than R. So in this case, still you cannot include it. So then what you can do, let's say not 11, we had 10. Okay. Let's say you had a 10 here. Now, 2, it was, no, we were not able to include. Then we added 2 plus 10. We got 12. Now still, now what happened? From less than L, you reached greater than R. Now you cannot include this 12. But what you can do is if you have 2 and 10, you can reject this 2 and include this 10. You can do that. Then 10 would fall in the range of 3 to 10 and it would be a winning combination. Now, here we can say that we are sure we would definitely reject 2. Why? Because if, let's suppose I'm saying 2 falls in some winning combination, then if it falls in some winning combination, it has to combine with some number which makes it to fall in the range of 3 to 10. But if it has a 10 next to it, which is making it to go par that uh, R value, then if even you include it and go further, you would have to include that 10 because we have consecutive groups. So like here we can conclude that don't we can never form a winning combination using this two. We would have to reject this two. Okay. So in this case of initial values 2 and 10, we are sure we would have to reject this 10, this 2. So what we would do, so once we reach greater than R, we would start rejecting from the left side. So we would reject this 2 and then again check. Now, if this 10 satisfied, we would take it. If it again doesn't satisfy, we would try to reject it from the left. And if it becomes empty, then okay, no problem. We would move further, move to the next number. Okay, so basically you can get a feeling that we are actually doing a two-pointer kind of thing there. Okay, so we are actually just taking 2 pointers and moving them. So what I'm actually doing here, okay, let's understand it more clearly from a good example. Okay, so if this, let's take this example. This is good to understand. Okay, so if we have this, what we are doing, we have this L and R range. Okay, this is our range. Now we would start a pointer. We would take 2 pointers I and J. Okay, we would start with, we would keep both pointers. Let's write it 10, 7, 5, 13, 8, 9, 12, and 7. Okay, what we are doing, first we would start with the first number. We would keep our pointer I also here, J also here. So now my J would be the pointer where my range is starting, and my I would be the pointer which would be moving ahead. So my range would be from J to I. Okay. Initially, I have the range from 10 to 10 only. So my sum initially would be 10. Okay. So I would check whether 10 falls in my L to R range, which is 12 to 25. Yes, 12 to 25. So I would first check whether 10 falls in this range of 12 to 25. No, it's less than M. So if this is less than L case, we would move our I pointer ahead. So we would move our I pointer here. Okay. Now we would include this 10 also. So sum would become 17. Now we would check whether 17 falls in this range. Yes, it falls. So now we can just pick up this range and increase our answer by 1. Okay, so we got our one range. So our answer would be initially 0. We would increase it by 1. Okay, so once we got this range, we can again reset both our pointers to this value. So I would also get here, J would also get here. We would again start from the next value. Okay, so my sum is 5 now. Now we would check 5, whether it falls in this range. Now we saw this is 5 is less than L. Okay, now we would move our I pointer ahead. Okay, so now 5 plus 13, we got 18 here. Now we would check whether 18 falls in this range. Yes, it falls. So we would take this range, 18, increase our answer by +1, move both our pointers I here, J here. Okay, now what we would do, our sum is 8 now. So we would check whether 8 falls in the range. No, it is less than L. We would move our I pointer. 8 plus 9 is 17. 17 falls in the range. We would increase our answer by +1. Again, reset. So I and J. Sorry. I here, J here. Okay, and then again 12 falls in the range. So again, we would +1 our answer. And then again reset I here, J here. Now 7 doesn't fall in the range. We would move our pointer I ahead. Once we reach out of the loop, we would stop. Okay, so like here 4 would be our answer. We got 4 groups actually. Okay, these 4 groups. This was the one group, second group, third group, fourth group. 4 was our answer. Okay, we did not got the excluding case here. So let's take another test case quickly so that we would understand. Yeah, in this we had some excluding case. Okay. Now, if you have take this case, what I'm doing, so you would start J here, I here. Okay, you have to keep the sum in between 7 to 9. And my initial sum would be, for 2, it would be 2. So 2 is less, we would move our I pointer here. So now 10 plus 2. Now what happened here? 10 plus 2, it became 12. Now for this range, like it's the same case which I had explained with 2 plus 10. With 2, it was less than L. With 12, it became greater than R. Now, once it happens like from less than L, you reached greater than R range. So you would start excluding from the start. So we'd exclude this 2, move this J pointer here. So exclude this 2, it became 10. Now we would check 10. 10 is still greater than R. So we are excluding until we get below R so that it comes in the range. Now we got 10, which is still greater than R. We would move our J pointer right. 10 minus 10, it became 0. So we have nothing in the range. This J, it became less than R, L. So once it becomes less than L, we would move our I pointer. So if the sum is less than L, we will move I pointer. If the sum is greater than R, we would move J pointer to reduce the sum and I pointer to increase the sum, as you can see. Okay, so it became less than L, we would move our I pointer and then it becomes 5. 5 is still less than L, again increase our I pointer. 6. 6 is still less than L, increase it to 9. So 9 is in this range of 7 to 9. It is an accepted range. So this is the first accepted range we got. So J was here. This is the accepted range. So answer becomes from 0 to 1. Now again, once we get an accepted range, we would reset both our pointers to the next number. We will start again from here. So 7 is again in the range. So we would increase our answer by 1, reset this to ij. Now 6 is not in the range. We would increase our I. 6 and 2, 8 is in the range. Increase answer by 1, reset both pointers to here. And this 3 is not in the range. Just increase this I. Once we go out, we would just break our loop. So the final answer we got is 3. These are the 3 ranges we got. Okay. 6 to this is not the range. These 3 ranges: 210, 513. Okay, 210 was also not there. It was 513, 7, and 6. These 3 ranges we got here. Okay. So I hope this thing is clear. This 2-pointer, how I am doing. If this is clear, we can move to the code part now. Yes, clear. Okay. So we just took the input NLR and the array A. Then what I did, I initialize these variables j with starting with 0, sum starting with 0, answer starting with 0, and our I pointer is moving from 0 to n. Okay. So in our outer loop, our I pointer is increasing by 1, and inside we would increase our j pointer. Now so when I got here, I have included this ith value. So I would do sum plus equal to ai. Now, if sum is less than L, we can just continue to next. So we can just in the next loop, again, I would get plus plus and would increase our sum. So we just did continue. If sum is below L, we have to increase our I pointer. Okay. Now, if sum is above L, now if sum is less than equal to R and greater than equal to L, it means it is in the range. If it is in the range, we would do answer plus plus. J would become I plus 1. So we would reset our pointers to I plus 1, and I would, like, if we are doing continue, I would get plus plus from our for loop, and it would also become I plus 1. So actually we are resetting both our pointers to I plus 1, and sum we are resetting to 0. Okay. So we did the reset thing and answer plus 1. Okay. Now if our range had exceeded R, what we would do? We would start removing from the j pointer. So until j is less than equal to I and sum is greater than R. So until sum is greater than R, we will reduce our sum by aj and increase our j pointer. So till the time sum is below R, we would do this thing. Sum is above R, we would do this thing. And once sum reaches less than R, we would check if now the sum is greater than L, which means we are in the range. We would do answer plus plus j equal to I plus 1 sum 0. So we would reset the conditions if the sum is like in the range. Otherwise, we would not do. So we will move to the next loop. Okay. So I hope this code is clear what we are doing through the two pointer, and we can just print the answer after that. Okay. So what the time complexity of this code would be? So you have an I pointer which is moving from 0 to n, and you have a j pointer. So in this while loop, this j pointer, at max, this j pointer would move from 0 to n. So we have two pointers which are moving from 0 to n. Overall complexity would be O of n. Okay. So
Sir, can you please explain the prefix sum with binary search approach also?
prefix sum is like, I have not thought of that approach as yet. So I can think of that and then only I can tell. Like in the while the contest, I came up with this approach only. So like maybe afterwards, if I can think of that, then I can tell. Or
Sure, sir.
those who have done it with that, you can like explain your approach in the chat so that others can see that. Okay. And like someone is writing segmentary approach. Segmentary approach, I don't know if it can be done with segmentary. So like I had come with this approach only during the contest. Now, if there may be other approaches also, so others can write down that, or if I get that, I can maybe comment that in the YouTube video. Okay. Can you explain like what you are telling to explain in short, Jay Kumar? Like this approach which I explained now, like is it not clear, or you're like, okay, in short, you like what part is not clear to you? If like entire thing is not clear, you can maybe rewatch it when it's uploaded on YouTube. Or if there is some part you can tell, turn on the mic and I can explain that part. Like it was this two pointer approach only. So we are taking two pointers I and j. Okay, like in short, if I would explain it, we are taking two pointers I and j. So we have an array. We are taking two pointers j and I. So j and I represents the range that my current sum is from the range of j to I, and we have a sum variable which is storing this current sum. So if this sum is less than L, then we would do I plus plus and increase our sum. If it is less than L, our current sum, we would do I plus plus and increase our sum. So if I moves ahead, the we would include more range and increase our sum. And if this sum is greater than r, it means we want to reduce our sum. So we would do j plus plus. And once j moves ahead, we would reduce our sum. And once this sum is in the range from L to R, if we get some I and j which is in the range from L to R, we would add that to our answer. We would add a plus one to our answer and reset both I and j to the next I plus one value. So from here, we would again start. So these are the three things I'm doing. Okay, so you can see from the code also that thing only I'm doing. So like if you did not understand, you can maybe rewatch when it's uploaded on YouTube. Or if you have some part which you are not understanding, you can tell. Okay, like is this approach clear to all? If you still have doubts, some doubts, then you can ask.
Yes, sir, clear.
Okay. Okay, so we can move to the D problem now. Okay, so in the D problem, what we have, Nikita loves mountains and has finally decided to visit the Berryland mountain range. And the range was so beautiful that Nikita decided to capture it on a map. The map is a table of n rows and m columns, with each cell containing non-negative integer representing the height of the mountain. He also noticed that mountains come in two types, with snowy caps and without snowy caps. So basically, you are just given a matrix, you can say a table, a matrix, where which represents the height of mountains. So you're given some numbers, and they are of two types. So every mountain would be either a snowy mountain or a without snowy mountain. So now Nikita is aware of this. He wants to sum of heights of all mountains with snowy caps to be equal to sum of heights of all mountains without them. So what Nikita wants to achieve is he wants the sum of heights of the mountains with snowy caps equal to the sum of heights of mountains with non-snowy caps. Okay, he has arranged the mayors of Verulandes to allow him to transform the landscape. Nikita can perform transformation on submatrices of. So now what? How can he achieve that? He can do transformations. So he can do transformations. He can select some submatrices of size k cross k. He can select a k cross k submatrix, and then he can add an integer constant c to the heights of the mountains within this area. So to all the mountains in the that area which is selected, a k cross k matrix, a constant c would be added to the heights of all those mountains. And but the type of mountains remain unchanged. Nikita can choose the constant c independently, and c can be negative also, and like so you can reduce also, increase also. C can be chosen independently, and it's also like it doesn't matter at what cost. You can just increase it to anything. Like even if mountain turn chaos having negative heights, you can also have negative heights for the mountains to achieve this thing. Okay, so that's what it's given. So to like understand the problem more clearly, let's take the first test case. And okay, so what we are actually given here, we are actually given this matrix. So this is actually here we are given a 3 cross 3 matrix, and we are also given a binary string, vector of binary string. What does that represent? So one represents a snowy mountain and zero represents a non-snowy mountain. Or if it was opposite, you can see that it doesn't matter. So one is snowy, one is non-snowy. So what you want to do, you want to make the sum of snowy equal to sum of non-snowy. Okay, that's what you want to achieve. So if you see here, what you have, like you can see, I am marking the snowy mountains with red. So this position is a snowy mountain. It means this is a snowy mountain, and this is a snowy mountain. It means this is a snowy mountain. Now all the remaining are non-snowy mountains. So what you want to do is the sum of snowy should be equal to sum of non-snowy. So what is the sum of snowy? It's 7 plus 2, and non-snowy is sum of remaining 11 plus 3 plus 4 plus 3 plus 1 plus 15 plus 0 also. Okay, so this is 9 here, and this is 14, 18, 21, 22, and 15, 37 here. Okay, so now this 9 is not equal to 37. We want to make them equal. That's our aim. How can you make them equal? It's given a value k. So this k is 2 here. So what you can do, you can select a 2 cross 2 matrix. Let's say you selected this 2 cross 2 matrix. Now, once you selected this, what you can do, you can add a constant c to each of the elements of this matrix. So you had 7, 4, 11, 4, 2. What you can do, you can add, let's say, take c equal to 1. Then what would happen? This 7 would become 8, 11 would become 12, 2 would become 3, 4 would become 5. So all of these 4 would be increased by 1. If you take c equal to -1, all of them would decrease by 1. If you take c equal to 3, all of them would increase by 3. So like whatever you would do, it would happen to all the 4 together. That's the thing. Or you could have selected this also. You could have selected this matrix also, or you could have selected this matrix also. You can select any 2 cross 2 matrix from here and increase the height of all of them by c. So you can do this multiple times also. Select different matrices, increase their height by c. And finally, what you have to do, you can do perform operations any number of times. And finally, what you have to achieve is make this sum of snowy equal to sum of non-snowy. That's the problem statement. I hope the problem statement is clear. Now, how can we do this? Okay, so the first thing to notice here is like if you have a k cross k matrix, so and the first thing you can just see the constraints of the problem first. So the constraints are n and m are up to 500, k is min of n and m. So the product of n and m would not exceed 2e5, 2.5e5. So like you have to do it in O of n into m and maybe some log factor. And you cannot go n square m square. Okay, so n into m, this whole matrix is approx 2e5. You can take it the sum for all test cases. And this k is min of n. So k cross k would again be of 2e5 order. So you have to do it in O of k or O of n into m kind of order. Now, how can you do this? The first thing is if you have some k, let's say k is 2 here. Now, what all groups can you select? What also, how many sub matrices are there which you can select? So you can either select this sub matrix. Okay. You can either select this or this or this. Like you have only 4 choices in this particular case. If you had a very big matrix, okay, of n cross m, and you had some k, okay, let's say you have some very big matrix of n cross m. This is n. At max 500 into 500 it would be. If you have, if you want to like think of all the possibilities of selecting a k cross k matrix, there would be, let's say k is something of this size. So this would be one matrix. Just move to the right by one step. This move to the right by one step. Move to the right by one step. This way you can move right one step. Then again move down one step. So if you move down one step, this would be. Then right one step. So the number of sub matrices you get where you can apply the operation would be of order n into n. If k is 1, you would get 1 n into n. At max, it would be n into m sub matrices where you can apply the operation. Okay. So you can just visit all those sub matrices. Now, what's the second thing that you need to notice? If let's suppose for this matrix, you applied the operation on this. Okay. So let's suppose you applied the operation on this submatrix. So if you are applying on this submatrix, what you want to achieve? You have some difference between this s and ns. Okay. So this is 9, this is 37. What's your final aim? You want to make this difference 0. If you look at it, it has currently a difference of 37 minus 9, a difference of 28. Your aim is to make this difference down to 0. Okay. So when you apply an operation, what change are you making to the difference? That's what you want to focus on. That's your final aim. Want to minimize this difference and make it zero. So if you apply an operation on this matrix, which I have marked with green, you can see there are two snowy mountains here, two non-snowy mountains here. So if you take any C, for the snowy part you would add a 2C, and for a non-snowy part also you would add 2C. So what's the change you are making on the difference? It's 2C minus 2C 0. So if you select this submatrix, whatever C you select, you would not change the difference. The difference would remain what it was. The change you are making is 2C minus 2C, which is 0. Okay. Now let's suppose you selected some other submatrix. Okay. Let's suppose you selected this particular submatrix. Okay. Now here, what change would you make? Here you can see there is one snowy mountain and there are three non-snowy mountains. So if you select some C, what would you add to the snowy part? You would add plus C to the snowy part. And what would you add to the non-snowy part? You would add plus 3C. What's the difference? What's the change you are making? It's 3C minus C, which is 2C. So you can make a change of 2C in the difference. So if you select C equal to 1, you can increase the difference by 2, or you can decrease the difference by 2 if you select it minus 1. If you select it 2, you can increase or decrease by 4. So you can see you can do plus minus 2, plus minus 4, plus minus 6. So you would move in the multiple of 2. You can make a change of a multiple of 2 to your difference using this matrix. So if you had a difference of 5, can you make it 0 just using this operation? No, you can't. You would either make it 1 or a minus 1, right? Making a change of 4 or 6. But if you had a difference, if this difference is 28, in this case only, what you can do, you can just apply, you can take C equal to 14, change the difference by 28, and the job is done. Okay, so the first thing you have to notice here is what changes you can make. So those changes would always be multiple of something. So if you select this submatrix, you can make changes in multiple of 2. If you select this submatrix, again 3 minus 1 is 2. Now how we got this 2? Was it clear? Like in this submatrix, there were 3 non-snowy, 1 snowy. Difference between them is 2. So 3 minus 1 is 2. So this is the 2. So in multiple of 2, we can make the changes. If you do a plus 1, you get plus 3 to snowy and plus 1 to non-snowy, a difference of 2. Plus 2 means plus 6 to snowy, plus 2 to non-snowy, difference of 4. You can understand that. So you would first go to each submatrix and find the changes you can make are multiples of what. So for the first submatrix, you cannot make any changes. It's 0. You can make changes in multiples of 0, you can say. For the second submatrix, you can make changes in multiple of 2. For the third submatrix, again, you have 3 minus 1 is 2. You can make changes in multiples of 2. For the fourth submatrix, again, the difference is 3 minus 1, which is 2. You can make changes in multiples of 2 only again. So you would go to each of the submatrix and just find those numbers whose multiples you can make changes. Now in this case, you only had 2. So it was simple. If the initial difference is an odd, like it's not divisible by 2, then you cannot. And if it is even, it is multiple of 2, then you can. Just yes or no, you can directly print. But let's suppose you had some, let's take the another test case only, you would understand from that. Here you had a 3 cross 3 matrix. So 3, 3, it was same. You can take this test case. 2, 1, 1, 2, 2, 2. This test case you can take. 3 cross 3 and 3 cross 3. Yes, you can take this test case. Okay. Is this some 2D prefix sum? Yeah, it is actually 2D prefix sum problem only. We will come to that, how to calculate it. Okay. Now let's take this test case. So what we have here, so this is our matrix, and let's mark the snowy things. This is snowy, this is snowy, this is snowy. Okay. Now let's see all the matrices. We have to take K is 3, so we have to take 3 cross 3. So we can take this as a 3 cross 3 submatrix. Now, what would be the what changes can you make here? You can see there are 1, 2, 3, 4, 5, 6 non-snowy and 3 snowy. So 6 minus 3 is 3. So you can make changes in multiples of 3. Okay. So from this you would select 3. So you can make changes in multiples of 3, you know. Now let's see the second submatrix. It has 2 snowy and rest non-snowy. So 7 minus 2, 7 non-snowy, 2 snowy is 5. So you can make changes in multiples of 5. Now you have 3 and 5. Okay, now you can calculate the difference, sum of 46, 31 and the sum of remaining. Okay, like I'm not going to calculate. Let's suppose the difference was, let's say, 53 or something. Okay, let's suppose the difference was 53. Now, can you reduce this difference 53 to 0 using multiples of 3 and multiples of 5? That's your problem. You can do multiples of 3x plus 5y, and if this can be made 53, and these x and y are integers and they can be negative also. That's the condition. So x and y belonging to integers. So this is like a mathematical relation. What you got is, if you can make this relation true using integers x and x and y can be negative also, positive also, then you can, if you can, then it's a yes, otherwise it's a no. Now, when can you do this? So how are you going to solve this problem? Okay, so x equal to 1, y equal to 10. Yeah, x equal to 1, y equal to 10, you can make it 53 in this case. Yes. So now how can you generalize this? Because you don't know what difference you would get, you have to write in terms of variables. So the first thing you can notice, using 3 and 5, like all the multiples of 3 would be done, all the multiples of 5 would be done, no problem. Let's say you have some 4. Can you make this 4 out of them? If you look closely, you can make 2 into 5 minus 2 into 3, 6. 10 minus 6, it would become 4. You can also make it. So what I actually did, I utilized 5 minus 3 and multiplied it by 2. So 5 minus 3 was 2. You so you can also do all the multiples of 2, because difference of 3 minus 5 is 2. You can also do all multiples of 2. And can you do 1 here? If you look closely, what you can do 3 into 2 minus 5. 6 minus 5 would be 1. So if you get a 1 here, it means you can just do all the numbers. So you can take 2 into 3 minus 5 multiplied by c. So if you want to get x, write an x here. It means you are doing 2x times 3 and x times 5. You would get x. So here actually you can get any number. If you can get a 1, you can get any number. That's what you have to realize. Now, like for any case, can it happen that you can never get a 1? Okay, let's, in 3 and 5 case, you can like make 1. You can always get 1. Like let's suppose you had 2 and 4. Can you get 1 from 2 and 4? Like by any combination? If you try to think, 2 is even, 4 is even. Either you add them, subtract them, whatever you do, you would always get an even number only. So you can never get odd numbers out of it, if you see. So you can only get multiples of 2. If the difference is odd in this case, you would give no. Now, how can we generalize it further? Like, let's say you had some 9 and some 15. Okay. Now, what all numbers can you make from them? Can you make a 1? Like if you can make a 1, you can make all the numbers. But can you? Like if you try to look more closely, and like here we are having two numbers, we may have up to n into m numbers, because there are n into m cases. In worst case, you can have n into m matrices, so you can have many numbers. Like you can have here 9, 15, 21, 30, like this. There can be many numbers which you can. Now, what would your answer be for this case when you have all these possibilities that you can take multiples of these? So here one thing you can notice, if you take the GCD of all the numbers, okay, so like till this time I was trying to explain the intuition. Like 2 and 4, if you know, the GCD of this is 2. 3 and 5, GCD is 1. And 9, 15, the GCD is 3. So like whatever you add, subtract, and do whatever, that would always be a multiple of 3. This is for sure. If you take 9 and 15, if you take all these numbers, then you would do GCD of all the numbers. GCD of all the numbers is 3. So whatever combination of these numbers you take, it would be a multiple of 3 for sure. You cannot make a 2 or a 1 out of any combination of these. You can just try and hit and trial and do that. And if you need a proof, what I can say, that if I am saying that GCD of all these numbers is G, let's suppose, it means all the numbers are some x1 times G, x2 times G, x3 times G, something like, let's say you have xn numbers, you have n numbers, I'm telling x1, x, and if you divide it by G, you get x1, x2, x3. So all the numbers can be written in the form of these. So whatever you do x1 plus x2g minus x3g, whatever you do, you can take a g common and some integers here. So the resultant would always be a multiple of the GCD of all the numbers. So what you have to do, once you got all the, once you checked all the possible sub matrices and got these numbers, the multiples of which you can reduce your difference by, you can take the GCD of all these numbers. And this GCD, if this GCD is, let's say, 3, it means if your difference is a multiple of this GCD, then your answer, if this is 0, it's a multiple, then your answer would be yes, else your answer would be no. Simple. That's what you have to check. Like, did you got the intuition what we are trying to say? Yes, and that's also reason, because GCD of AB is equal to GCD of B minus A. Yeah, so like a, a small proof I provided through this thing, like you can write all the numbers as a multiple of G, then whatever plus minus you do, that would be a multiple of G. You can take a G common. So you would always get a multiple of G only. So you can make all the multiples of G out of this. So the difference should be divisible by these, then you would get a yes, otherwise a no. So that's what you have to do here. Now, nice proof. Okay, need optimal way to find all numbers. Okay, so now the only target is that only. How can you optimally, like for each submatrix, how can you compute that number? So the thing we need to do, so if we go to this submatrix, what we need to calculate, how we calculated that, we calculated 9 minus 6 equal to 3, sorry, we calculated 6 minus 3 equal to 3. That's what we do, because we had 6 numbers which were non-snowy and 3 numbers were snowy. So we want to keep the count of snowy numbers minus the count of non-snowy numbers for any submatrix. So how can we do this optimally? So you can obviously use a prefix sum here. So a 2D prefix array. If you compute a 2D prefix array, where you, for a 1, you would do a plus 1, for a 0, you would do a minus 1. Okay. 0 can be replaced by a minus 1. So if you replace these zeros by minus 1, and compute a 2D prefix sum array, Then you can just go to each value, and like if you went here, you can plus k here, plus k here. So you can take this from I plus k to j plus k, like I to I plus k, and like I to I plus k. Okay, like if it is an I comma j, sorry, if you are an at I comma j, you would take your square from ij to I j plus 1, I plus j plus k, I plus k to j plus k, and I plus k j. Okay, so these would be the endpoints of your submatrix that you got. So at every ij, you can check for this submatrix. So if you have pre-computed your 2D prefix sum array using +1 -1, then now using that you can compute the sum of this particular part, and the whatever sum you got, you can put that into a pet maybe. Okay, so like you may get for 2 3 times, you may get 3 3 3. So you don't want to repeat, or you can repeat, or instead of putting set, just like outside only you can initialize a variable g with 0 and just take gcds there only. Okay, so you can just take gcd of all those numbers during that time also, or you can just put them in a set and take it outside. Okay, you can do it during that time only, no need of set. So that way you can compute the GCD of all those submatrix sums you got. And once you get that GCD, then you can just check. You would also have to calculate the initial difference. Okay, so first thing you calculated the G using that. Next thing, you would just go to every element uh, from this matrix. For this matrix, you would go to every element. If it is snowy, you would do plus. If it is non-snowy, you would do minus. That way, so if it's 46, you would do plus 46, and 49, you would do minus 14, like that. Anyone you can do plus, and one you can do minus. And the final difference you get, you can do the absolute of that difference. And then you have to just compute whether this difference is divisible by 0, divisible by G. That's what you need to just check. Okay. Now, if you have a little doubt, how can you do the 2D prefix array? Like if you have not uh, done 2D prefix array in past, so like I will try to explain a little how can you compute that. Okay, so if you, let's take this example only. If you have this matrix, okay. So if you have 1 0 0 0 1 0 0 0 1, or you had more. Okay, let's take more. Okay. So let's say you have this matrix. You want to compute the 2D prefix sum array. So what I'm going to do, I'm going to take my a 2D vector, okay, 2D vector of size n here, m here. Okay, we would take a 2D vector of size n cross n. And what my prefix ij would represent, it would represent my sum. So if let's say my ij is this, I'm at this. So my prefix ij should represent the sum of this whole thing. So if I am at any ij, it should represent the sum starting from 0 to I and 0 to j. This rectangle, it should represent the sum of this rectangle. That's what we would pre-compute in our prefix array. How can we do that? So first we would, first thing we are doing, we would replace all the zeros with -1. Okay. So if you have a 0, you would do -1, not 0, because we want to compute the difference between 1 and 0. Okay. So you would do a -1. So instead of 0, you can either like make all the 0 -1 here only, or just while computing, you can just check if it is 0, do a -1. If it is 1, do a +1. Okay. So I'm not changing it to -1 here, but we would do -1 if it is a 0. Okay. So first thing we would do, uh, we would initialize our prefix array, okay, with zeros. Let's say we have all zeros. Yeah, yeah, you can do also total count of 1 minus total count of 0. That also you can do. You can do take two prefix arrays, one having count of 1, one having count of zeros. You can subtract that. That's also okay. Okay. So now what I'm doing, this is my prefix array. At this place, I'm definitely going to have only the 1. So I would initialize with this. So I would take a 1 year. Now I would move like this. And first thing I would do is I would compute a 1D prefix array for each row. So for each row, I would do a 1D prefix array. So 1, and then 0 is a -1. So 1 minus 1 is 0. So I would write a 0 over. Then 0, and this is a -1. Okay, this is a -1. So 0 minus 1 would become a 0 here. -1 here. Okay. Now -1, again a -1, we would get a -2 here. Okay. So now we have a 0 here. It, so again, for the second row, we would again do a 1D prefix array computation. Like we can forget the first row for now. For each row, first we would do, then we would like try to compute for the, we would move column wise after that. So first we would move row wise. So this is computed for first row. Now second row, it's starting with 0. So we would start with -1. This is not 0. This is actually -1. Now then we have a 1. So for 1, we would do a +1 and it would become 0 only. Then we have a 0. So 0 minus 1 would become -1. Then we have 0 minus 1 would become a -2. Okay, so second row is computed. Likewise, we can just compute for the third row and the fourth row also. Okay, so third row, it would start with 0. It means it starts with -1 plus -1. It means -2, and then a +1. So 1, then a -1 again. So -2. Then start with 0. It means start with -1. Then again -2, -3, -4. So we have computed our prefix array for each row. Now here what it's storing, any prefix array storing is the sum of this. This prefix array storing sum of this. This is storing sum of this. Now what we needed, for this we needed the sum of this whole. So what we can do, first row you had the sum till here, next row you had sum till here. So to this we can add this above 1. So in this way we can again do the prefix something. So now this would include this thing. So then with this we would add this. So this would include this thing. So we would now move column wise and do the again prefix something. So 1 would remain 1, then 1 minus 1 would become 0. So column wise we would sum up. Column wise what we are doing, actually we are doing prefix ij. Here what we did in the first step, like first step we are moving like in this way, column inside row. So we were doing prefix ij is equal to prefix ij minus 1, like plus equal to. Okay, this we were doing. Now in the second case, now what we are doing, prefix ij plus equal to prefix I minus 1j. This is what now we are doing. So 1 had become 0. Okay, so now 0 minus 1 would be -1, -1 minus 1 would become 2. So 0, 0, 0 is 0, 0 minus 2 is -2, -2 minus 2 is -2. So 1 and then -1 would be -2, -1 would be -3, -3, -6, -2 to -4, -4 minus 2 is -6, then -4 becomes -10. So this way, now we have computed our 2D prefix array, where each prefix ij represents the sum of this whole thing. Now, how would you compute the sum of k cross k rectangles? So let's say you are at this ij. Now you want to compute, your k is 3. Okay. You want to compute for this thing. Okay. So for any rectangle, let's say you are at some in middle here. Okay. This is 1, 1 for a zero based indexing. This is 1, 1. So you have this rectangle you want to compute. This is ij. This is I plus k. Sorry, this is I and j plus k. This is I and j plus k. Okay, and this is I plus k, j plus k. Actually, it is I plus k minus 1 and j plus k minus 1. So this is I then plus 1 plus 2. So you can see it is -1 instead of first. Because we have to take a length of k only. So this first one would be j would be 1 length, j plus 1 would be 2 length. So j plus k would be, you can understand, j plus k minus 1 would be k length. And then this would be I plus k minus 1 and j. So these are the boundaries of my rectangle of the prefix sums what I'm trying to calculate. Now, how can you do the sum of this? So what you can say, like you had this inside a rectangle. So you can say my prefix of this has this sum, this whole sum. From this, I can subtract this part, subtract this part, and now since we have subtracted this part 2 times, we can add this part. Okay, so what I'm doing this minus this and plus this. That's what I am doing. So I would just do prefix of I plus k minus 1, j plus k minus 1. This thing we are adding. Then this thing also we are adding plus prefix of like this before this. So we have to add before this thing. So it would be I minus 1, j minus 1. And then what we are subtracting? These two rectangles. So this particular rectangle and this particular rectangle. So we are subtracting. So this thing would be prefix of I plus k minus 1 and j minus 1. So just before this we are subtracting. Okay, it would be j minus 1 and minus prefix of here it would be in. So I minus 1 and j plus k minus 1. So this would be our value at for the ij to I plus k and j plus k for this k cross k rectangle. The value that we get would be this thing. So this formula we can compute. Okay. So once we have computed, you can just take the GCD of this value. G is equal to GCD of G comma value. You can take this GCD, you can compute this for all the values. You can compute the GCD and then sum and all you can compute. Okay, is this clear? The place not needed, we can come PS, this is okay. So you can one you are missing just one step. Yeah, what you have written. Okay, I hope now it is clear now. Okay, so we can move to the code now. Okay, so what I'm doing, first I took the input NMK and then the matrix A, I took the input and then this vector of string, 10 vector, the binary string, I took that input. So all the input are taken. Now I would take a prefix, a 2D prefix array of size n cross m. Okay, I have taken a 2D prefix array of size n cross m. Now first thing I would, for every row, I would compute the prefix array. So I'm going to every row there. If my value is 1, I would do a 1, otherwise a minus 1. This would be my initial value. Then from 1 to m, I would do prefix ij equal to first prefix ij minus 1. And then if it is a 1, the current value would be plus plus, otherwise minus minus. Okay. So this was the previous value. And then we are adding either a plus 1 or a minus 1, depending on the string. So through this, we have computed the prefix 1D prefix array for each row. Now we would make it a 2D prefix array by moving column wise. So we are moving column wise, column out in the outer loop, rows in the inner loop, and prefix ij plus equal to prefix I minus 1j. So like this way, we are computing our 2D prefix array. Okay. So this is the code how we compute a 2D prefix array. Now, here what I did, I took a set and inserted it inside, but you can just directly take the GCD without using a set also. Okay. So now what we did, we want to compute our value. Now we would move for every, so from I we would move till n minus k plus 1, because if you have a matrix of, you can understand that if you have a matrix of n cross m and you want to form k cross k subgroups, so if k is somewhat of this size, like if this is your first, your last one would be like the last that you would compute would be somewhere here. So this would be, this thing would be n minus k, this thing would be m minus k. Okay, this would be the last matrix that you would compute. If you move here and try to compute this, it would go out of range. Okay, so you would run your outer loop only till 0 to n minus k only, and 0 to n minus k only. Okay, and then you would compute a value. As I told, what formula I had written, I written this formula. Prefix I plus k minus 1, I plus k minus 1, j plus k minus 1. We included that I plus k minus 1, j minus 1. Now, the next thing, we are doing subtracting this thing, but we have to check that this j minus 1 should not become negative. So if j is 0, we would not subtract this thing. Okay, so then it would be 0. So one more way to do, like, if you don't want to check this, you can take a one based indexing. If you take a one based indexing for your 2D prefix array, then this at minimum j would be 1, so you would have 0 here. You can initialize it with 0, so you would do minus 0. You won't need to check this, but I prefer taking, if it's 0 based, I prefer taking 0 based, so there is no confusion. Okay, you would have to do conversions of my vendors to 0. So I can just check if j is greater than 0, then do minus. Again, for this case, if I is greater than 0, then do this I minus 1 j plus k thing. So this subtraction thing I did. Now, one more term we didn't did is this I minus 1 j minus 1. For this, if both I is greater than 0, I is greater than 0 and j is greater than 0, we did plus this. Okay. Now, if this value is greater than 0, then only we'll insert it in set. If the value we got is 0, so multiples of 0, it means we cannot change anything. So like, why do GCD with 0? It won't affect our answer. So like, if it is greater than 0, then only I'm inserting it into a set. Okay, now I'm computing the difference. Okay, so for difference, we just again iterated through the whole matrix. And if it is a 1, we would do difference plus aij. If it is else, we would do difference minus aij. Okay, so this way we would compute our difference and we'll take the absolute of our difference. Okay, so is this thing clear? And now I'm computing my GCD, so I took g equal to 0. So for whenever you are doing GCD of some numbers, you would always initialize your variable with 0, because GCD of anything with 0 would be anything. So GCD of 0 comma x is x only. So it won't affect our answer. Okay, that's why we initialize with 0. If you take 1, then GCD with 1, you would always get 1. So like for multiplication, you initialize with 1. For addition, you initialize with 0. Likewise, for GCD, you initialize with 0. Okay, we did GCD for iterated through the set and the GCD of all. You, instead of taking the set, you could have done this GCD thing here also. Instead of inserted, you could have taken g equal to GCD. This statement you could have written here and g equal to 0. It was okay. Okay. Now, if the difference is 0, first thing is difference is already 0. We don't need to do anything. We can just print yes. So I am printing C out yes here. If the difference is already 0, we don't need to. We just print yes and return. Now, if the GCD is 0, GCD is 0, it means we had no numbers in our set. There was no value. All the values were 0. Okay, all the submatrices were 0. So if GCD is 0, we cannot change our difference. And if difference was 0, we already printed yes. We are coming to this case, it means difference is not 0. And our GCD is 0, it means we cannot change the difference. So we will print a no here. So in this case, we would print a no. And now for the remaining cases, we would just check if difference modulo GCD is 0, we would print a yes, otherwise a no. If this thing is 0, we would print a yes, otherwise a no. Simple. Okay, so is the problem clear, code clear, everything is clear? If there is any more doubts in this problem, you can ask, or we can end the session. Okay, it's clear. So thank you very much. So, and hope you liked it.